Hi, in this video, we are going to continue our course on number theory. And today I want to show you four problems which are quite interesting and hopefully you can learn from these questions. So the first one is find all primes P and Q, all primes P and Q such that P plus Q is equal to P minus Q whole cube. So this is my question. It is very simply stated, but we have to find primes which satisfy this condition. Okay. So the first step in these types of questions is always like think about taking modulo a particular number. Here, since we are using primes P and Q, my first idea could be take modulo P. If you take modulo P on both sides of this equation, you will end up with Q is congruent to, this will become minus Q cube modulo P. Why? Because this expansion is P cube minus Q cube minus 3P square Q plus 3PQ square. So if you see, the three terms here are divisible by P, and the only term that is not divisible by P is minus Q cube. So therefore, by taking modulo P, you will get Q on the left hand side and minus Q cube on the right hand side, right? So this implies that Q plus Q cube is congruent to 0 mod P, right? So therefore we know that P must divide Q plus Q cube, or P divides Q times Q square plus 1. And basically from here we could conclude that since P does not divide Q, P divides Q square plus 1, right? Okay. So we'll keep this in mind, and now we take the other thing, we take modulo Q for the original equation. If you take modulo Q on the original equation, you will get P is congruent to, from here, every term here, the last three terms are divisible by Q, so it will be Q is congruent to P cube. P is congruent to P cube mod Q, right? So once we have this, from here we can deduce the same things. P minus P cube is congruent to 0 mod Q, which basically implies that Q divides P times P square minus 1, right? Great. Now we have these two results that we have gotten. Now let's work it out on the next screen. So since we know that P plus Q is equal to P minus Q whole cube, that means obviously P plus Q will divide P minus Q whole cube. So this means that P minus Q whole cube is congruent to 0 mod P plus Q, right? Any two numbers which are equal to each other, you can say that any one of them is divisible by the other. So we can say P minus Q whole cube is congruent to 0 mod P plus Q. Now think about P minus Q. P minus Q is actually equal to P plus Q minus 2Q. So if you think about P minus Q, that is congruent to minus 2Q mod P plus Q, right? Taking mod P plus Q on both sides of this equation, it is obvious that P minus Q is congruent to minus 2Q mod P plus Q. Therefore, in this equation, we can say that this side is minus 2Q whole cube is congruent to 0 mod P plus Q, right? So basically we are getting minus 8Q cube is congruent to 0 mod P plus Q, or we can say that P plus Q basically divides 8Q cube, right? So P plus Q divides 8 times Q times Q times Q, and we know that GCD of P and Q is 1 because both of them are prime numbers. Therefore, it implies that GCD of P plus Q comma Q will also be 1, right? This is by simple application of Euclid's division lemma. So this is correct. GCD of P plus Q and Q is 1. So that means P plus Q and Q are relatively prime to each other, right? So that means P plus Q cannot divide Q, and there are three Qs here. So it implies that P plus Q must have divided 8, right? P plus Q must divide 8. So if P plus Q divides 8, we are getting basically P plus Q could be one of the divisors of 8, which is 1, 2, 4, and 8. And since P and Q are both primes, you cannot have P plus Q is equal to 1. You cannot have equal to 2. You can have them equal to 4, but in that case, P and Q will both be equal to 2, right? And it will not satisfy the original equation. If P and Q are both equal to 2, this is not true, right? So the only option left for us is P plus Q is equal to 8, which means P and Q, the ordered pair must be 3, 5, the two primes, right? So actually, what we did initially when we took mod P and mod Q, we didn't get anything major from there. However, if you took mod of P plus Q, you are getting nice results here, and we are quickly able to solve the problem, right? So the lesson from the problem is sometimes try taking modulo different numbers. You may or may not get something useful. And we ended up taking mod of P plus Q, and that turned out to be the way you solve the problem, right? Let's move on to the next question. This is question 2. Here we have given, this is a strange question. I mean, not very difficult, but looks strange. Given 34 factorial, value of 34 factorial is given 2952 3279 9039 A. This digit is unknown and it is called A. And after that, there is 0414 0847 6186 0964 35 B, and then there are 7 zeros. So basically, two digits are unknown in this whole value of 34 factorial in the decimal notation, right? Your job is to find A and B. So relatively is very straightforward, but you have to think of a good idea by which you can try to find A and B here, right? So we know that 34 factorial is a product of the first 34 integers. The first 34 integers. So we know for sure that 9 divides 34 factorial, right? And 9 divides 34 factorial, then we can use divisibility criteria of 9. Divisibility criteria for 9 is that the sum of the digits must be divisible by 9. Must be divisible by 9. So that gives us a good equation. If you take the sum of all of these digits here, we are getting A plus B plus 136. And we know that 9 must divide that, because 9 will divide 34 factorial. And the sum of the digits is this. So from here, we can immediately say that A plus B must belong to either 8 or 17. If you add 8 to 136, you get 144, which is divisible by 9. And if you add 17, you get 153, which is also divisible by 9. You cannot take A plus B to be anything bigger than 17. You cannot take it anything lesser than 8. You cannot take negative values because these are digits on decimal notation. The digits values will be going from 0 to 9, right? We have 0 is less than equal to AB less than equal to 9. And we have A plus B must be 8 or must be 17, right? So that is the first thing that we can say. Another divisibility criteria that you could use here is that 11 divides 34 factorial, because 11 is one of the integers that comes in the product of 34 factorial, right? So 11 divides 34 factorial. Now, what is the divisibility criteria for 11, right? So what you need to do here is find the alternating sum. Alternating sum means that you take first plus and then minus. Find the alternating sum from left to right for all the digits. From left to right for all the digits. So basically, what do I have to do? I have to do something like this: 2 minus 9 plus 5 minus 2 plus 3 minus 2, and so on. Find the alternating sum. And if the alternating sum from left to right for all the digits in decimal notation is congruent to 0 mod 11, then the overall number is also divisible by 11, right? So if you do this calculation, you will end up getting something like this: 11 must divide 77 plus A minus 59 plus B, which becomes 11 divides 18 plus A minus B. Now that means A minus B could be minus 7 or could be 4, right? A minus B could be negative here because the difference between the digits could be 7. That's possible. And earlier we had gotten A plus B could be 8 and 17, right? Now you have to take all the possible cases here. A minus B is minus 7, A plus B is 8, and see what are the possibilities. See what are the possible numbers for A and B. You will realize that there are two solutions that come. A and B ordered pair could be 6, 2, or it could be 5, 12. Obviously, we'll reject this solution and we'll say that 6, 2 works because A and B are ultimately digits in a decimal expansion of a number, right? So it cannot be more than 9. So our answer finally will be A and B have to be the ordered pair 6, 2. I have left out some steps in the simplification here, which you can clearly work out. You have to take different cases. A minus B can be minus 7, A plus B can be 8, and see what comes. And similarly, A minus B can be 4, and A plus B can be 8, and so on, right? So once you try that out, this is the only valid solution that comes. So the idea in this problem was what? We checked divisibility of 34 factorial with any integer less than 34. And the two integers that help us get a good criteria is divisibility by 9, divisibility by 11. You could also check divisibility by smaller numbers, but 9 automatically assumes, say, divisibility by 3 and stuff, right? So that is an interesting problem. Let's move to the next one. This is the third one. Given three distinct natural numbers A, B, C, show that GCD of AB plus 1, BC plus 1, and CA plus 1 is less than equal to A plus B plus C by 3. So that is the problem. Okay, so let's think about it. We don't know the GCD of this, so let's assume let D is equal to GCD of AB plus 1, BC plus 1, and CA plus 1. We have to show that D is less than equal to A plus B plus C by 3. Now, this implies that D divides AB plus 1, D divides BC plus 1, and D divides CA plus 1. So that means A basically AB, BC, and CA, AB, BC, and CA all must be congruent to minus 1 mod D, right? Think about it. D divides this, so AB plus 1 must be some K times D. So AB is equal to K times D minus 1. So if you take modulo D on both sides, we are getting AB is equal to congruent to minus 1 mod D. Similarly for BC and CA also, right? So we get this result: AB, BC, CA are congruent to minus 1 mod D. So now we can say that AB minus BC will be equal to B times A minus C, and that should be congruent to 0 mod D, right? If you subtract two numbers which are congruent to minus 1 mod D, when you subtract them, they will be congruent to 0 mod D. So B times A minus C is congruent to 0 mod D. This is what we are getting so far. Now, think of if B and D have a common factor, Let's say B and D have a common factor, and let's call that common factor P, and P is greater than 1, right? then we know that P divides D, and therefore, and D divides AB plus 1. So we know that P divides AB plus 1, and we have also said that P is a common factor of B. So P divides B as well, right? So that means we have P divides AB plus 1 and P divides B. So that will mean that P will divide AB plus 1 minus A times B, right? Because this is also divisible by P and this is also divisible by P. Therefore, P will divide all that. So when you subtract AB from here, we get P divides 1. So which means P is equal to 1. Basically, what we have shown is that B and D cannot have a common factor. The common factor P must necessarily become equal to 1, right? So we are getting B and D are co-prime. This is very important. Similarly, so if B and D are co-prime, if you think about it, here we know that D divides B times A minus C, right? B times A minus C is congruent to 0 mod D. So therefore, D divides B times A minus C. And now D and B are co-prime. So we get D divides A minus C, right? It follows from here that D divides A minus C since D is co-prime with B. And similarly, we can also prove that D divides A minus B and D divides B minus C. And you have already shown D divides A minus C, right? The proof for these two follows exactly the same process. You will assume that P divides D divides BC plus 1 and P divides C, for example. Like just follow the same steps that we use to get this, right? So once we have these conditions, what you know is that A and B and C are all congruent to each other modulo D, right? Because if D divides A minus B, then A is congruent to B mod D. And similarly here, B is congruent to C mod D. We are getting this result now. A, B, C are congruent to each other modulo D. So without loss of generality, we can assume that let's say A is greater than B is greater than C, right? So they are congruent to each other. So they are multiples of each other, and A is greater than B is greater than C. So we can write this as A is greater than equal to B plus D. If A is the next multiple after B, it at least must be equal to B plus D, or it could be even higher, right? All of the three, A, B, C, are multiples of D, and we have assumed that A is greater than B is greater than C. So we can say that A is greater than equal to B plus D, and similarly, greater than equal to this is greater than equal to C plus D, right? Since B is greater than equal to C plus D, we can write this, so which is equal to C plus 2D. So what you are getting is A is greater than equal to B plus D is greater than equal to C plus 2D, right? Now think about it, A plus B plus C, what can we say? That will be greater than equal to, since A is greater than equal to C plus 2D, we can write that here. And B is greater than equal to C plus D, so we can write that here, C plus D for B, and plus C as it is. So this is equal to 3C plus 3D, right? So we are getting A plus B plus C is greater than equal to 3C plus 3D, which is clearly greater than equal to 3D, right? So now we have A plus B plus C divided by 3 is clearly greater than equal to D, right? So we have proved our statement. All we had to do was get to the situation that we got A and B and C are all congruent to each other modulo D. After that, we assumed that there is some ordering among them. A is greater than B is greater than C, and we can establish inequalities like this, which helps us come to the conclusion, right? I have one last problem that I want to look at. We have briefly discussed it before, and this states something like this. This is Wolstenholme's theorem. Wolstenholme's theorem. I have discussed it in short once before. I will outline the proof of this theorem here. So let's say let P is greater than 3 be a prime. Prove that if 1 plus half plus 1 by 3, so on till 1 by p minus 1 is equal to m by n, where m and n are co-prime, where m and n are co-prime, then p square divides m. This is what we want to prove. So let's think of this side here. This is the summation of I goes from 1 to p minus 1, 1 over I, right? And we are saying that that is equal to m by n. Now, instead of trying to work with this, I will start by working with twice of this. Twice of I is equal to 1 to p minus 1, 1 over I. Because when I do that, I will be able to group it nicely. I will say I is equal to 1 to p minus 1. This is the same thing as 1 by I plus 1 by p minus I. What do I mean by this? Basically, when you write the terms twice, you can group 1 by I with the other one, right? So I will write 1 plus half plus 1 by 3 plus 1 by I plus 1 by p minus I, and this goes on to 1 by p minus 1. And I write this again, but this time I write it in a reverse order. And I write it like this, p minus I plus, this becomes 1 by I, and this goes on till 1 by 1, right? I have written two different series. They are the same series. So I'm saying twice of this is equal to the sum of this, where I'm doing a vertical summation, right? I'm doing this vertical sums here. So this is my general term, 1 by I plus 1 by p minus I, right? So the reason we are doing this is twice of this p minus 1, 1 by I is written as summation I goes from 1 to p minus 1, 1 by I plus 1 by p minus I. And if you simplify this, this becomes I times p minus I, and on top you get a p. I goes from 1 to p minus 1. You can take the p outside, p times summation I goes from 1 to p minus 1, 1 by I times p minus I, because p is a constant and summation is over I. And now you think about modulo p of the thing inside the summation, right? So if you think of modulo p of this term, right? This term is becoming I goes from 1 to p minus 1, 1 by I times minus I mod p, right? So this is basically minus 1 by I square summation I goes from 1 to p minus 1 mod p, right? So we can put the minus sign outside and we get minus p summation I goes from 1 to I min p minus 1, 1 by I square mod p, right? Now what is this 1 by I square? It is like saying take the inverse of each prime number, 1 by 1 square plus 1 by 2 square plus 1 by p minus 1 square. But if you are doing modulo p, you should realize that this is the same thing as writing I inverse square. What is I inverse? So if you think of p as a prime number, let's say 5, think of all the numbers 1, 2, 3, 4, right? What is the inverse of 1? 1 inverse is 1. What is the inverse of 2 inverse? 2 inverse is basically going to be 3, because 2 into 3 gives 6, which is 1 mod 5, right? So 2 inverse is 3, and 3 inverse will be 2, because 3 into 2 is 6, which is 1 mod 5. Basically, you are saying what is the AX should be congruent to 1 mod P, right? Then we can say that X is congruent to A inverse mod P. That's what I'm saying. So when you look at all of these numbers, 3 inverse is 2, 4 inverse would be 4 times 4 is 16. So 4 inverse will be 4 only, right? So when you look at 1, 2, 3, 4, the inverses are 1, 3, 2, 4, right? So when I do I inverse square, think about it, that will come out to be 1 square plus 3 square plus 2 square plus 4 square. And that is the same thing as doing the sum of the I squares, right? Mod P. So what I'm saying is this summation is the same as minus P summation I goes from 1 to P minus 1 I square mod P. The sum of the squares of the inverse of all the primes from 1 to all the numbers from 1 to p minus 1 is the same as the sum of the squares of all the numbers. Like summation I square is same as summation of I inverse square. You can see that very easily in this example. For p is equal to 5, summation of I square would have been 1 square plus 2 square plus 3 square plus 4 square. Whereas when you do inverses and when you square the inverses, that is coming the same but in a different order: 1 square, 3 square, 2 square, 4 square. So that is the logic behind this step. And once this step is done, the problem is done basically. We have minus p summation I goes from 1 to p minus 1 I square mod p. And this summation I square mod p will basically be the expansion by the formula p minus 1 p 2p minus 1 by 6. And we have to do this modulo p, right? And there is a minus p outside also, right? Now think about it. This whole integer, this whole thing is an integer, is an integer. Why is this an integer? Because it is sum of squares of integers, right? So it has to be an integer, right? Now, what we can say is that p minus 1 multiplied by 2p minus 1 divided by 6 is also an integer, is also an integer, because because p and 6 are co-prime. P and 6 are co-prime. If you do p by 6, there is no common factor that you can cancel here because p was a prime greater than 3. So p is 5, 7, and so on. P and 6 are co-prime. So if the whole thing was an integer, then it was an integer because this part was an integer, right? And if this part is an integer, that means we can say that the whole expression is minus p square times p minus 1 2p minus 1 by 6, and which is an integer. So it is clear that the whole expression is divisible by p square, right? So this is congruent to 0 mod p square. So what we have gotten is that twice of the summation of 1 to I is congruent to 0 mod p square, right? Which proves what we wanted to show. We wanted to show that p square divides m, right? So we have gotten the conclusion. So that is the proof of your Wolstenholmes theorem, right? That's about it for today's video. I wanted to show you some of the problems here. We'll continue with more problems on number theory. If there is uh, any theory element that we have to discuss, we'll get to that as well. But stay tuned for more problem solving sessions. This just continues our course where we are doing all sorts of questions in number theory so that you are well prepared for the upcoming Olympiads. So I'll see you next time.